So now the time is 6 o'clock. As usual, we will wait for a couple of more minutes and we will start at around 6:02 or 6:03. Okay. I hope I am audible and you all are able to see my screen. Thanks. So as I told in the last class, today we will be discussing some questions from previous year GATE EC exam that are related with linear algebra, mainly related with questions related with matrix. Okay, so um, I will. You can see some of the questions. These are pretty straightforward questions. No explanation itself is needed, but still, I will go through those questions so that you will get to know what are the kind of question that has been asked previously for the GATE exam. Okay, so anyway, we will wait for 1 more minute and we will start. So basically, today the concepts that we are going to use are mainly these three. Okay, so I hope all of you are familiar with matrices and their determinants. So this second part is well known, I hope, to everyone. Determinant of a matrix, right? So then at least some of you may be quite familiar with eigenvalues and eigenvectors and also rank of a matrix. So these are the preliminaries required to solve the question that we are going to see today. Okay, so it's the time is 6:02. So anyway, we will quickly start these preliminaries. Then we will move on to one question after the other. Okay. So first of all, you all know what a matrix is, right? For example, A equal to some matrix 1, 1, 1, say 2, 0, 1, 1, 2, 3, right? It's a matrix, right? What is the size of the matrix? This is 3 by 3, right? So 3 rows and 3 columns. So now say this matrix 1, 2, 3, 4, 2, 4, 6, 8. So what is the size of this matrix? This, 2 by 4, right? There are 2 rows and 1, 2, 3, 4 columns, correct? So for a matrix, if number of rows equal to number of columns, the matrix is told to be a square matrix, right? So for square matrix, we can define determinant, right? So you all will be knowing how can we calculate the determinant of a matrix. For a 2 by 2 matrix, there is a fairly simple way. If the matrix is say A, B, C, D, then say I will call this matrix as capital A, then determinant of A, sometimes it is denoted as A within 2 lines. So just like modulus of some number, modulus of A or determinant of A is nothing but A into D minus B into C, right? Product of diagonal elements minus product of off diagonal elements. This is for a 2 by 2 matrix. For bigger matrices, you can calculate the determinant. That's what I believe. So today I'm not going to deal how to calculate determinant. And now again, for a square matrix, we can define something called eigenvalues and eigenvectors. Okay, before that, some more very basic stuff. Identity matrix or identity matrices. What are identity matrices? I will denote identity matrices with I, say suffix n. That means there are the size of the matrix is n cross n. So that is the small n. So in the matrix, the diagonal entries will be ones and all the other entries will be zeros. So for example, I2, that means identity matrix of size 2 cross 2 is 1, 0, 0, 1. And I3 is 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so these are very known facts to everyone, I hope. Now, yeah, coming to eigenvalues. Eigenvalues and eigenvectors. So usually these two things, eigenvalue and then eigenvector, will come as a combo, as a corresponding to every eigenvector there will be an eigenvalue, and vice versa, you can say. Okay, suppose A is an n cross n matrix. That means it's a square matrix of size n cross n. For such a matrix, suppose all the entries are real numbers. Okay, this R denotes real. Power n cross n means just the size of the matrix. Okay, don't get confused with the notation. Just the meaning is that all the entries in the matrix A are real numbers. Okay, for simplicity we can assume that. And suppose there exists a vector x belongs to Rn, need not be in Rn, it can be in Cn as well, size of n cross 1. It's a vector of size n cross 1, or it's a matrix of size n cross 1. You can visualize in any way. Belongs to, this is complex numbers. You have to be very careful here. The matrix is in real field. I am defining the entries to be real, but the vector x is defined to be, it can have complex entries as well. Okay, then if A into x equal to, for some scalar lambda into x, lambda is again a complex number. It's a number. It's not a vector, not a matrix. It's a number. Ax equal to lambda into x. If we can find such a lambda and an x, okay, then lambda is known as the eigenvalue of A, and x is known as the corresponding eigenvector. Okay, so now I will state a fact. For a n cross n matrix, for an n cross n matrix, we can find n eigenvalues. There will be n eigenvalues for an n cross n matrix. Okay, so now in this n eigenvalues, some of the eigenvalues can be the same. That means, for example, I will take a matrix. So this will imply another important property. Say this is the matrix that we are looking for, say 0, 2, 0, 0, 0, 3. What is the speciality of this matrix? This is a diagonal matrix. That means only the diagonal entries are non-zero and all the other off diagonal entries are zeros. So these kind of matrices are known as diagonal matrices. For diagonal matrices, these diagonal entries itself give the eigenvalues. So the values of this matrix are 1, 2, and 3. Okay, so there are 3 eigenvalues for this 3 by 3 matrix. So here, suppose the second entry, if it was instead of say 2, if it was 1, then again there are 3 eigenvalues, but note that the eigenvalue 1 is repeated 2 times, right? But the total number of eigenvalues is nothing but 3 itself. Correct? Now, the next thing. Again, first we told what a determinant of a matrix is, right? Now, suppose the matrix is A, then determinant of A can be written as the product of, this is for any square matrix, the property that I'm going to write is valid. Okay, determinant of A is nothing but the product. Pi denotes the product. Okay, from I equal to 1 to n lambda I. That means the product of all eigenvalues will give the determinant of that matrix. Okay, for example, for this matrix, what is the determinant? That is 3, right? It's very easy to compute. Correct? The determinant of the matrix is 3. Also, the product of eigenvalues is also 3. Correct? And also, one more property. Trace of A will give the sum of eigenvalues. I equal to 1 to n. This is summation. What is trace? Trace means the sum of diagonal elements. Okay. These two things will look very trivial if you take the matrix A to be a diagonal matrix. But in fact, these two properties will hold for any square matrix. Okay. Is it clear? For any square matrix A, size n cross n, the determinant of that matrix is nothing but the product of the eigenvalues. There will be n eigenvalues, and trace of the matrix is nothing but the sum of the eigenvalues. Okay. Now we will come to the very important concept of rank of a matrix. So this may be defined as, this rank is not only defined for square matrices, the rank of a matrix is defined for any matrix of size m cross n. M need not be equal to n. That means number of columns need not be equal to number of rows for the matrix that we are considering. For any matrix, we can define rank. Rank of a matrix is defined as it's a number. Okay, it's an integer. It's a positive or it is a non-negative integer. That means rank can be 0, 1, 2 up to minimum of m comma n. Okay. For a 5 cross 6 matrix, what is the maximum rank that is possible? Can somebody tell? Yeah, correct. It is 5. So the maximum rank possible is 5. It can be anything between 0 and 5. Okay. It can be 0, 1, 2, 3, 4, or 5. Okay. Now, what is the definition of rank? Rank is defined as the number of linearly independent columns, or this is same as the number of linearly independent rows. Okay. So if you take and study some abstract book, they will define rank in two ways. Initially, they will define it as column rank. That is the first definition. Then they will define it as row rank. Okay. Then finally, they will show that column rank and row rank of a matrix are same. That means rank of a matrix is the number of linearly independent columns, or it is same as the number of linearly independent rows. Okay. So I'm just going through the definition. While solving the problems, you can I can give more explanation how to calculate the rank or how can we find the rank of a matrix. Okay. So now up to this, yeah. Now again, come back to square matrices. That means the size that we are considering is again n cross n. Okay, square matrix. Now, for a square matrix, the maximum rank possible is, as you know, it is n, right? The rank between anything between 1, 0, 1, 2 up to n. So now, suppose if one eigenvalue is 0, okay, then what is the determinant of the matrix? Determinant of the say the matrix is A. Okay, determinant of the matrix is nothing but the product of the eigenvalues, right? Suppose if one eigenvalue is 0, then the product of the eigenvalues is 0. So the determinant of A will also be 0. Suppose lambda I equal to 0 for some I. Okay, then determinant of A will be equal to 0. So instead of that, going in the other way. I am saying that determinant of A not equal to 0. What does that mean? That means none of the eigenvalues are 0. Is that correct? Everybody agree with that? If determinant of A is told to be non-zero, then none of the eigenvalues are 0. Correct? Okay. Such matrices are called full rank matrices. So you can have lot of other terminologies for the same matrix. If determinant of A not equal to 0, then the matrix is full rank matrix, or in other words, the rank of the matrix, rank of A equal to n. That is the maximum possible rank, right? That means if a matrix is told to be rank deficient, that means the matrix is not full rank matrix. That means at least one eigenvalue is 0. Is that clear? I hope it makes sense to everyone. Yeah, very good. So now, yeah, we have seen a lot of things. I know some of you may not be able to like cope up with the pace. Now we will see some questions. Initially, we will start with very elementary matrix questions, not even related with this rank or any stuff. So we will see one such question, then we will increase the difficulty of the question. Okay, all the questions are related with matrices only. And one more thing, unlike I think at least few of the names are familiar to me. I have seen in the previous classes. So unlike the last classes, I will not be solving the question as such. That will be very difficult for this, like questions related with matrices. You need to observe the question very carefully. Okay, so computing the rank, there is a systematic procedure to do that, but that is very time consuming. There is something called Gaussian elimination method and all, but that is very time consuming process. By observing the matrix, at least in the questions that are coming in the gate exam, you can tell the rank of the matrix by just observing the matrix. Okay, so you have to be very careful while seeing the questions. Now we will get into the very first question. This is a question that appeared in 2014. Okay, sorry, 2014 gate EC exam. As you can see, this is question number 1. Okay, there were 4 sessions in 2014. This is from session 1. Okay, so this is the first question that we are going to see today. So there are, I will read the question. For matrices of same dimension m and n and scalar c, which one of these properties does not always hold? So there are 4 properties given. If some of you know the answer, you can simply tell the answer, because there is nothing to solve in this. This is like properties of the matrices. The first property, this notation implies transpose of a matrix. Transpose, I can like explain. All of you may be knowing this. 1, 2, say 3, 0. Okay, the transpose of this matrix is nothing but 1, 3, 2, 0. What am I doing here? Say I have the matrix A, which is equal to A11, A12, up to say A1n. Here I have say A21 up to AMN. Okay, it's a normal matrix, a rectangular matrix. Here AMN. These are the entries. Okay, so A transpose, say A is M cross N, then A transpose will have a size N cross M. Okay, N cross M, and the entries will be A11, A12 will come here. Okay, here A12 in A transpose, it will come here in the second row, first column. Here it was in first row, second column. Just interchange that position, that ordering. That's it. So I'm just explaining for the sake of completeness. I know all of you know this. So this is nothing but this is AM1. Okay, so this is AM1, this is AM2, and AMN. Correct? So this is the transpose operator. So now, is the first property true? A transpose or M transpose the whole transpose, is that equal to M? That is correct, right? I am doing the same operation twice means I am putting, 1 second, I will take that back. Yeah, so A transpose whole transpose means what? I'm again picking these things back. A11 I am taking, that will be in the same position. A12 I will again put back to this position. Like that it will go, correct? Sorry, not A1, A12, A1n. So it will come again as same as the matrix A, correct? Is that clear? So the first property is very trivially true. So now consider the second property. So C is a scalar. I am multiplying the matrix with a scalar, means I am multiplying each element in the matrix with C, and I am taking the transpose of the resulting matrix. Is that equal to C times M transpose? They are equal, right? You can see here, I am multiplying C before C. Multiplying a matrix with the scalar means I am multiplying every entry with C. C, 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 correct? If I multiply with C before taking the transpose or after taking the transpose, that doesn't make any difference, correct? So this will again be equal to, the second option is also correct. Those two are equal. Okay, and the second property is, again, it's a property of matrices. A plus B, the whole transpose is equal to A transpose plus B transpose. Similarly, one more property, A into B, the whole transpose equal to B transpose times A transpose. So these two you can keep in mind. You can prove, like, you can see the proof anywhere. If you search in internet or if you see any textbook, you can get the proof of these two. The first one is very elementary. You can just take two matrices just like this and you can see that. And this needs some more tools to prove that. Okay, so the third property is also correct. So which one is the incorrect option? That is definitely the last one. The last one is incorrect. M into N. So I will erase some of these things. M into N is not equal to N into M in general. Okay, you can take an example and you can see this. M into N not equal to N into M. Matrix multiplication is not commutative. I can take an example and I can show you. Say 1, 1, 1, 0, and very easy matrices. 2, 0, 0, 0. What is this product? This is equal to 2, 0, 2, 0, correct? Instead of that, say I'm taking 2, 0, 0, 0 into 1, 1, 1, 0. What is this product? This is nothing but 2, 2, 0, 0, correct? So what does this mean? They are not equal. So you can find some examples in which they are equal, but in general, they are not equal. M into N not equal to N into M in general. Okay. So what does that mean? The answer is option D. You need to find the incorrect option, or which one of these properties does not always hold. Okay. So I hope it is clear. If you are having some doubts, you can ask now. Otherwise, we will move to the next question. Again, next question is also fairly straightforward. We need to use a property again corresponding to the determinant of two matrices. Is that clear? The first question. If you know the definition of transpose, then there is nothing in that question. Yeah, great. So now the question is, I hope you can see this is 2014. Again, set 1. I hope, I think this is from set 2. This question is from set 2. Okay, not from set 1. This is from set 2. Okay, yeah. So now the question is like this. The determinant of matrix A is 5 and the determinant of matrix B is 40. The determinant of matrix AB is. So determinant of A is given as 5 and determinant of B is given as 40. And again, I'm using a property that I'm not going to prove here. This requires a good amount of tools to prove this. Okay. So determinant of A into B is nothing but determinant of A into determinant of B. So you have to know this property. Okay, determinant of the product of two matrices is the product of the determinant of the matrices. Okay, now it is very easy, right? Determinant of AB is equal to 200, 5 into 40. Is that clear? There is nothing to be, you have to use this property. That's the only key takeaway from this question. I hope it is very straightforward. Now we will go to a slightly more taxing question. So this question is related with eigenvalues of matrices, eigenvalues of matrices. Okay. So this question is not entirely correct. I can at the end of this I will show why am I saying so. But still, let us try to solve this question. Okay. A real 4x4 matrix A satisfies the equation A square. A square is A into A is equal to I. That is identity matrix, where I is the 4 cross 4 identity matrix. Now the question is to find the positive eigenvalue of the matrix A. Okay. How can we find that? One very easy way is A square equal to I means, say I take this matrix, identity matrix itself, 0, 1, 0, 0, 0, 0, 1, 0, all these are, this is an identity matrix, I4. Okay, I4. So I into I is again I, right? I square is I. I square is I into I, which is equal to I. You can see. It's from this, what can you say? They are saying A is some matrix. A can be identity matrix as well, right? What are the eigenvalues of this identity matrix? Identity matrix is a diagonal matrix, correct? For a diagonal matrix, the eigenvalues are the diagonal entries. So here, there are 4 eigenvalues. All the 4 eigenvalues are plus 1, right? The positive eigenvalue of A must be equal to 1. So that is one way of answering the question. But if you want, I can see the actual way of solving this. Okay. So we need, it is asked to find out the eigenvalue of the matrix A. That means, say lambda is the eigenvalue, Ax equal to lambda x. This is the fundamental equation to find the eigenvalues, right? Ax equal to lambda x. So now we know A square equal to I. We will left multiply this equation with A. That means A into Ax equal to A into lambda x. Lambda x is a vector, okay? Lambda is a scalar and x is a vector. So I will write a bar. Okay. So A into Ax is nothing but A square into x. Lambda into Ax, A into lambda x can be written as lambda into Ax. Correct? So what is A square? That is I. I into x equal to lambda into Ax. Correct? Again, Ax is what? Ax is lambda x, right? Ax is lambda x because Ax is lambda x. So I into x is again x. X equal to lambda square into x. What does that mean? Lambda square equal to 1. Lambda equal to plus or minus 1. Is this clear to everyone? So this is the very convenient way of answering that question. We can simply visualize some matrix and we can write the answer, because this should be correct for all the matrices, right? Such that A square equal to I. Otherwise, the question will be incorrect. If the question is having multiple answers, then the question, it's not a multiple choice question as well. It's a and like numerical answer type question. If the question has multiple correct answers, then these gate authorities, they will give mark to everyone. Okay, otherwise they will cancel the question. So you need not worry about that. If you have a matrix that has this property, a square equal to I, and you are sure that the matrix has an eigenvalue plus 1, then definitely this is going to be the case. Eigenvalue is 1. Now, yeah, sometimes you got here lambda equal to -1 as well, correct? For some cases, say the matrix is -1 0 0 0 0 -1 0 0 0 0 -1 0 0 0 0 -1. So for this matrix as well, suppose this is A, then A square is nothing but I, right? Correct? A square equal to identity matrix. Does this matrix has any positive eigenvalue? No, right? All the eigenvalues are -1. So it doesn't have any positive eigenvalues. Such cases are possible, but in the question, unfortunately, they are not even bothered about that. Okay. So anyway, to solve the problem, +1 is the correct answer. Is that clear to everyone? Can we go ahead to the next question? Question number 3. This is again, yeah, a question related with eigenvalues. Again, you can solve this question in a very easy way. I will zoom the question a little bit. Okay, so a matrix is given. Suppose I'm calling this matrix some name A. Okay, and is asked to find out the minimum eigenvalue of the matrix A. So can somebody tell the answer? So one way is to calculate Ax equal to lambda x, then taking this to the left side, Ax minus lambda x equal to 0. What does that mean? A minus lambda I is the identity matrix, into x equal to 0. Correct? And equate the determinant of A minus lambda I equal to 0. And you will get a, since this is a 3x3 matrix, you will get a cubic equation on lambda, and you can solve that cubic equation and you can get 3 values of lambda. That is the standard procedure. That's the standard way of finding the eigenvalues of a matrix. Okay. But is there somehow you can, so this will take at least 5-6 minutes to solve, because cubic equation you may not be able to solve very easily. Correct? If it's a quadratic equation, you can use the formula minus b plus or minus root of b square minus 4ac whole divided by 2a, right? What will you do if it's a cubic equation and you do not know any of the roots? That's a problem, right? You will be stuck. So that is not the way to solve this problem, to approach this problem. One thing you can observe here is that here all the options, they are 0, 1, 2, 3. There are no negative values. These eigenvalues can be any negative number as well. Okay, there are no negative values or negative integers or negative real numbers are coming as the options. Correct? So if you can convince yourself, or you can prove that, or you can show that 0 is one of the eigenvalues of the matrix, then you are sure that the minimum eigenvalue is 0. Correct? Everybody agree with that? Anyway, in the options, you cannot find a number that is less than 0, right? If you find 0 as an eigenvalue of the matrix, then 0 is the answer. Everybody agree with that?
Sir, I didn't get this, sir. Can you please repeat, sir?
Yeah, sure. So A is a 3x3 matrix, right? A will have 3 eigenvalues, correct? And if you see the options, there are 4 options given. And we need to find it's asked to find the minimum eigenvalue, correct? Suppose I do not know all the 3 eigenvalues, but instead of that, I find that 0 is one of the 3 eigenvalues. If I say that, then do you agree that 0 is the answer to the question?
Yes, sir.
Correct?
Sir, maybe it might be 1, 2, and 3. The minimum
No, 1 and
eigenvalue
2.
could be
No, 1 is greater
more
than
than
0,
0.
right? 2 is also greater than 0. 3 is also greater than 0. If I know 0 is an eigenvalue of the matrix, then 0 is the minimum one, right?
Yes, sir. If we know that, but we don't know here.
Yeah, that's what. That's what I'm saying. If somehow we get that 0 is the eigenvalue, okay, that somehow I will clarify that we have already discussed in the initial 5 or 10 minutes, that I will come again. Okay, so if if you are convinced that 0 is one of the eigenvalues, okay, then 0 is the answer to the question. That you agree, right? How will we show 0 is one of the eigenvalues is a different question that I will show. But if I show you that 0 is one of the eigenvalues, then 0 is the correct answer. That everybody agree with?
Yes, sir.
Yeah. Okay, very good. So now, what does 0 is an eigenvalue means? It's a rank deficient matrix, right? If 0 is an eigenvalue, then it's a rank deficient matrix. You can see here, correct? If determinant of A is 0, that's a rank deficient matrix. Correct? What happened? It's a rank deficient matrix, right? Yeah. So now you can see the question, right? Yeah. If we can show that A is a rank deficient matrix, then 0 is an eigenvalue, correct? Now, how can we show that A is a rank deficient matrix? We need to show that the rank of A is less than 3. It can be 2 or 1. It cannot be 0 anyways. If rank of a matrix is 0, meaning that all the entries in the matrix are 0. Okay, that is one thing that you have to keep in your back of the mind. Okay, so yeah. Now, what is the definition of rank? Rank is the number of linearly independent columns or number of linearly independent rows. What does this linear independence means? Say I have 2 or say 3 vectors. See v1, it's a vector v1, v2, v3. Okay, then linearly independent means v3 cannot be written as the linear combination of v1 and v2. You cannot express v3 as the linear combination of v1 and v2. Linear combination means I am weighing the vector v1 with some scalar a, and I am weighing the vector v2 with the scalar b, and I am adding those things. Then if you can't get v3, then we will say they are linearly independent. If you can get v3, say I will give you an example. Say these are the 3 vectors 1 0 0 0 1 0 0 0 1. So are these 3 vectors linearly independent? So can you write say 0 0 1 as the linear combination of these two? That means a into 1 0 0 means a 0 0 0 plus 0 b 0, right? So this is equal to a b 0. So is this possible? Can this and this be equal? That means 1 equal to 0, the third element, third entry. It is not possible, correct? So they are linearly independent. Is that correct? Now come back to this matrix. In this matrix, can somebody tell some linear relation among the columns of the matrix is?
Sir, column 2 is the sum of column 1 and column 3, sir.
Exactly. Exactly. That means there is some linear dependence. Correct? If you can find a linear dependence among the columns, then the column rank cannot be equal to 3, or the rank of the matrix cannot be equal to 3. It is 2 in this case. Say two vectors are, suppose in a 3 by 3 matrix, again I will give some examples. A is a matrix. Suppose rank of A is 0. Okay, A is 3 by 3. Rank of A is 0 means very simple. All the entries are 0. Okay. Now rank of A is equal to 1. That means there are two possibilities. Either I have, say, some non-zero column and all the other columns are completely 0. This is one possibility. Otherwise, there is some other possibility. Say I have some column, say you can, some real number R1, R2, R3. These are integers, or these are real numbers. It can be 0, or it can be negative numbers, it can be positive numbers, it can be anything. Okay, R1, R2, and R3. So I'm having some C such that the columns are like this. Say C here, some D here, DR1, DR2, DR3. So this is some other possibility. This means the second column can be written as the scalar multiple of first column. That means C times the first column will give the second column. D times the first column will give the third column. Here rank is 1. I will give you an example. 1, 1, 1, 2, 2, 2, 3, 3, 3. So here rank is 1, correct? Because the second column can be expressed as the, or second column is 2 times the first column, and third column is what? 3 times the first column, correct? Or if you see row wise, all the rows are same, correct? First row into 1 is second row. Again, first row into 1 is third row. That means again a scalar multiple of first row is the second row and third row, correct? So that means rank is 1. There is only one independent vector. This is that one vector, 1, 1, 1. If you see column wise, this is that independent vector. All the other columns can be expressed as the scalar multiple of the first column, correct? That is one way. That is that are the possibilities for rank equal to 1. Now rank equal to 2 means, rank of A equal to 2 means, again, say I have two columns, R1, R2, R3, and say S1, S2, S3. Now the third column is, say, A times R1 plus B times S1, A times R2 plus B times S2, A times R3 plus B times S3. That means I am weighing the first column by a factor A and weighing the second column by a factor B, and I am taking the sum. That is the third column, correct? For example, say I have the, and also one thing, S1, S2, S3 and R1, R2, R3 are linearly independent. That means you cannot express S1, S2, S3 as the scalar multiple of R1, R2, R3. That is there. Okay. So, yeah, I will again give you an example. Say I have a matrix 1, 0, 0, 0, 1, 0. Okay, and third column, what happened? Yeah, third column is, say, 5, 6, 0. What is the rank of this matrix? Five times first column plus 6 times second column is the third column, right? Everybody agree with that? Here the rank is 2. So rank equal to 3, that means full rank means all the 3 columns or all the 3 rows are linearly independent. Agree? Okay. So now coming back to the question. Anyway, there is a linear dependence. First column plus third column is the second column. Or in another way, you can say second column minus first column is the third column. Anyway, you will get a linear relationship, right, between the columns. First column plus third column is second column, as you have identified. Correct? That means there is a dependence. This is not full rank. The rank of the matrix is, rank of A is equal to what? Is it 3?
2.
Yeah, it is equal to 2. What does that mean? This is not a full rank matrix. What does that mean? The determinant of A is 0. What does that mean? That means 0 is one of the eigenvalues. Does everybody agree with that?
Yes, sir.
So does everybody agree with the fact that 0 is the answer to the question?
Yes, sir.
Yeah. Anyway, I am not sure whether 0 is the answer or not, because I have not found out the remaining 2 eigenvalues, because the remaining 2 eigenvalues can be negative numbers as well, that I do not know. But from the given options, you can deduct the fact that 0 is the answer. Correct? Because the remaining 2 eigenvalues, the non-zero eigenvalues, can be say -1. That I do not know. Correct? I have not shown that. But given the circumstances or given the options, I am convinced that 0 is the answer. Okay? Everybody agree? Okay. Now we have some very interesting questions. Okay. I think we are running short of time, but still I will try to do as fast as possible. Okay. Now, is the question visible to everyone? This is again from 2014. Yeah, this is a matrix. They have called it as J6. It's a 6x6 matrix. Okay. So I will write it. I think it's not very clear. This matrix is obtained by some permutation applying on the identity matrix. What does that mean? Say I have the matrix like this. Okay. So this is the matrix given J6. Only 6 elements are non-zero. They are 1 through this off diagonal, and all the other elements are 0. Now they are obtaining some matrix P, which is equal to I6 plus alpha times J6, where I6 is the identity matrix of size 6 cross 6. Okay, so P equal to I6 plus alpha times J6. Now what? Yeah, alpha is a non-negative real number. It is given. Okay, the value of alpha for which determinant of P equal to 0. Again, determinant of P equal to 0 means what? This is a rank deficient matrix. Correct? Now let us write P anyways. Identity matrix, all of you know, right? I'm not going to write that. Anyway, I will write 1 0 0 0 0 1 0 0 0 0 0 0 0 1 0 0 0 0 0 0 1 0 0 0 0, and the last column all zeros but 1, plus alpha times J6 is nothing but wherever we have 1 here, okay, we need to replace that with alpha. Correct? 0 0 0 0 0 alpha, alpha, Correct? If I make some mistake, please let me know. Okay. Yeah, this is alpha times J6. Now the sum P is equal to, it's a big matrix again, 6 cross 6 matrix, 1 0 0 0 0 alpha 0 1 0 0 alpha 0 0 0 1 alpha 0 0 0 0 alpha 1 0 0 0 alpha 0 0 1 0 alpha 0 0 0 0 1. Now, can somebody tell the answer very quickly? What is the value of alpha such that the determinant of P equal to 0? You can in fact make the rank of the matrix to be equal to 3. That's a hint that I'm giving. It's very easy. You can see these two columns that will give you the answer. Can we make these two columns the same? For what value of alpha, the third and fourth columns are same? I can't hear anything.
For alpha equal to 1.
Exactly. When alpha equal to 1, you can see that this column is, say, I'm erasing this. This is equal to 1 and this is equal to 1. What does that mean? The third and fourth columns are same, right? Similarly, here this will become 1, this will become 1, this will become 1, and this will become 1. Correct? What does that mean? There is a linear dependence. Again, you can see first and sixth column are same, second and fifth column are the same. Correct? So they are linearly dependent. There is some linear dependence. That means the matrix is not full rank. Correct? That means determinant of P equal to 0. At least one eigenvalue is 0. So determinant of P equal to 0 for alpha equal to 1. So the answer to the question is alpha equal to 1. Does everybody agree with that? Any questions? Can I go ahead? Everybody on the same page? Thumbs up or thumbs down? Okay. I hope it's clear to everyone. If you're having some questions, please unmute yourself and you can ask, or you can type down in the chat window. Okay, please explain. Okay. Okay, I will write the matrix P again. These are alphas. Okay. Now, here in this matrix, we need to, the question you can see where alpha is a non-negative real number. The value of alpha for which the matrix P has determinant equal to 0. That is what is asked to find out, correct? So here, determinant of P equal to 0, what does that mean? It means that the matrix P has at least one eigenvalue which is equal to 0, correct? Or in other words, the matrix is rank deficient. That means this is not a full rank matrix, correct? The matrix is rank deficient means, it means that there is some linear dependence among the columns of the matrix, correct? So some columns are linearly independent. Maybe one or more columns can be linear, two or more columns can be linearly dependent, correct? So here, one simple observation. So that's what I told in the beginning of the class. So I cannot prove these things, but you need to observe these things. Then I can, if alpha equal to 1, then determinant of P equal to 0. That's what I'm saying. Okay. So here, if you see, observe these two columns. Okay. The third column and fourth column. Suppose, as you have pointed out, if alpha equal to 1, then those two columns are exactly the same, right?
Yes, sir.
Yeah. That means, say I'm calling it as column 3 as V1 vector, sorry, not V1, V3, and this as V4. If they are equal to V3 equal to V4, that means there is a linear dependence. That means the matrix is rank deficient, correct? It's not a full rank matrix. That means determinant will become equal to 0. That means when alpha equal to 1, determinant of P equal to 0. So what is clear now? It is clear that when alpha equal to 1, determinant of P equal to 0. So it is asked to find out a non-negative real number alpha such that determinant of P equal to 0. So the answer is 1. Is that clear now? I am not showing that if alpha equal to say 2, 3 or something. Okay, in that case, determinant of P can be equal to 0. That I do not know, that I am not even seeing. Okay, that I am not even trying to look at. What is the reason? I got one value of alpha for which determinant of P equal to 0. And I am hoping that that's the only answer. If there are multiple answers, that's not my headache. That's the headache of whoever is making the question or whoever is evaluating the exam paper or the gate exam. Correct? So, are you convinced that when alpha equal to 1, determinant is 0?
Yes, sir.
Yeah, great. Now we will move to one next.
Sir, in this case, we chose third and fourth columns.
Yeah.
But in general, what, sir? The middle columns should be equal.
No, nothing like that. Any two columns. Any two columns.
Any two columns should be equal to.
No, not even equal. That's what in the previous question we have seen, right? In that case, there is no equality, even though here determinant of A is equal to 0, right? In the previous question, I hope you remember the question. Determinant of A equal to 0 in this case. Here there is no equality among the columns, but there is some linear dependence. Linear dependence means you can write this column, the second column, as the sum of the first and third columns. So what is the very
linear dependence should be.
Yes,
considered.
exactly.
Okay.
The very trivial linear dependence is nothing but being equal. Correct? One column equal to other column is they are very trivially linearly dependent. Correct? Say I can write V3 as 1 times V4. Correct? Or maybe all the other columns you can weigh with 0. That's the definition that I have given here, right? So one column as the linear combination of other columns. In this case, if you want me to write like that, you can write when alpha equal to 1. Okay, when alpha equal to 1, V3 equal to 1 times V4 plus 0 times V1 plus 0 times V2 plus 0 times V5 plus 0 times V6. I can write like this, right?
Sir.
Yeah. Since they are 0, I am not even considering. That's it. Those things will not come into the picture. So I hope it makes sense. So I think I have the remaining two questions are not very easy. They require some more time to solve, but still, let's see. We will quickly see the question. Yeah, you can see the question, right? Let A be an M cross N matrix and B an N cross M matrix. One is M cross N and the other one is N cross M. It is given that, determinant of IM. IM means identity matrix of size M cross M plus AB equal to determinant of IN plus BA, where you can see A of size M cross N, B of size N cross M, then AB will be of size M cross M, right? And BA will be of size N cross N. This is N, okay? N cross N. Is that correct? So you can add these things. IM means M cross M matrix. AB is again size M cross M. This is a different matrix, identity matrix plus AB. And this is a different matrix, identity matrix of size N plus matrix BA. And it is given that this is, in fact, it's a weak property. It's a property that is there in matrix theory. Okay, it is given. You can use this property. Okay, and it is asked to find out the determinant of this matrix using this property. Okay. So is the question clear to everyone? Is it clear to everyone? So in fact, we can find the determinant of the matrix in the usual way that you do. If you compute that, you will get the answer. Okay. So you can do that way as well, but they're asked to find out the determinant of the matrix using this above property. That means if you use this property, then you should be able to compute the determinant very quickly compared to the usual method. Otherwise, there is no point in using these properties, right? So does somebody has any intuition, or by seeing this matrix, you are getting some idea? If you are having some, you just unmute and you talk. Otherwise, I will answer the question. Okay, anyway, if you use the property, you can find the determinant of some I m plus ab. Correct? So it is asked to find out the determinant of this matrix. Correct? What does that mean? What does that mean? That means that this matrix should be equal to Im plus AB. Correct? The given matrix. This much you can very easily deduct from the question 1, 1, 1, 2. Correct? From this, what do you get? M equal to 4. Correct? That's very straightforward because the matrix is of size 4 cross 4. Correct? Now, what is AB then? Im plus AB is this. Then AB is 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Correct? Up to this, do everybody agree?
Yes, sir.
Correct. So AB is a 4 cross 4 matrix, right? So how can we get this matrix? By some A and B that is of size, say some size. This is A is of size 4 into some n, B is of size n into some 4, right? AB should be equal to this. Correct? So if you can find such A and B, you can find B into A and plus identity matrix size n, and you can find the determinant of that. That will be equal to the determinant of this. Correct? It seems pretty complicated, correct? But in fact, if I give you A and B, this will become very simple. Okay, so A is equal to 1, 1, 1, 1. B is equal to 1, 1, 1, 1. This is 1 cross 4 and this is 4 cross 1. Is AB equal to this matrix? That's equal to that matrix, right? I hope everybody know matrix multiplication. Does everybody agree A into B is, if I take A as
Yes,
this
sir.
and B as this, AB is equal to this, correct?
Yes, sir.
Yeah. So now it is very straightforward. Now n equal to 1, right? So determinant of I plus I4 plus AB. This is what we need to compute. This is the given matrix. I4 plus AB equal to determinant of n equal to 1. I1 is nothing but a 1 plus B into A. Correct? This is the property. Now what is B into A? 1, 1, 1, 1 is the B matrix, and 1, 1, 1, 1 is the A matrix. What is A into B? Sorry, B into A. this must be a 1 cross 1 matrix. That means that must be a number. Correct? What is that number?
4.
Yeah, correct. Exactly. This is equal to 4. So determinant of I is nothing but 1. This is equal to B into A is 4. So it's equal to determinant of 5. That means determinant of a scalar number is nothing but 5 itself. So the answer to the question is 5. So if you find out the answer brute force or in the direct way, you can compute the determinant of the matrix, then you will get 5 itself that I had verified anyways. So the answer to the question is 5. If you want to convince yourself, you can try to find out the determinant yourself. So does this question clear to everyone?
Sir.
Yeah. So here again, as you told in the beginning of the class, it's not about solving the question. You need to observe the question very carefully in the questions that are related with matrix theory. So there will be direct methods by which you can compute the answer. Just like in this question, you can find the determinant. But if you can find out the correct A and B, then finding the answer is just multiplying these two vectors, these two very simple matrices. Correct? But otherwise, the question will take around 10 minutes to solve, or maybe 5 or 6 minutes to solve. So I prepared for one more question, but maybe we will do later this question. Okay. So this question uses a completely different idea, not related with, anyway, it is related with eigenvalues, but some other theorems you need to use. You may be familiar with, I don't know, perhaps you may be familiar with Cayley-Hamilton theorem. So if you use that, you will get this answer. This is also, in this question also, you can see the question, right? You need to express A cube, where A is this matrix, A cube in terms of the matrix A itself and the identity matrix. You can find A cube and you can try to plug in these 4 equations. Only one of these 4 choices will give the correct answer. You can verify that and you can find the answer. But there is a very elegant way of doing this, very simple way of doing this, if you apply the correct theorem. Okay, that again, you can save few minutes. That will be, these few minutes will accumulate to say some 15-20 minutes. That will be a bonus to solve other questions. That's the way all these objective exams go on. Okay, so far so good. Any questions from any of the 5 or 6 questions that we had done today? If not, we will wind up the today's session. We will wind up the session and we will meet again next Tuesday. Next Tuesday, I'm asked to do some questions related with probability theory. After that, I will stick with communications and signals and system. As somebody asks, I will do questions related with Fourier transforms, DFT and all. Okay, so I will be more focused on signals and systems afterwards. But anyway, in the next week, I'm asked to do some probability related questions. Okay, if you are having some previous year questions related with these topics, you can share with me so that I can do that in the coming classes. Okay. Any questions so far? Okay, then let's wind up the session.
Sir.
Yeah, go ahead.
Sir, are there any resources to find these tricks? Formulae?
No,
Like,
formulae, there are no formulae that we had used today, right? Whatever
like you said, some determinant formula. Determinant of AB equals to determinant of A into determinant of B.
Oh,
Like those things.
such things you can find out in any matrix theory textbooks. One textbook that I can tell you is Linear Algebra by Gilbert Strang.
Gilbert's?
Strang.
Okay.
Right. Gilbert Strang.
Okay, sir.
Yeah.
Sir, and these tricks, some few tricks you have used, no, sir?
Which
Like
trick?
that. Like linear dependence.
Linear independence, everything, linear dependence,
We are
everything. Those
we are
things will
directly
be
using.
those things will be in this book, Linear Algebra by Gilbert Strang. Linear Algebra. This is the name of the textbook. The
Okay, sir.
author's name is Gilbert Strang. He's a professor at MIT. So this is a very basic level linear algebra textbook. Okay. So you will see lot of details. You will see lot of examples. Everything you can see in this textbook. Okay. But for
Okay,
GATE exam, you do not need to study the textbook in its completeness. You can refer to some handbooks or something. For I do not know which handbook is better or better than the other. I am no one to recommend that. So I do not know about that. But if you want to study linear algebra, this is the Bible of linear algebra. Okay.
okay. Thank you.
Yeah. Thank you.